Okay guys, now I want to talk to you guys a little bit about our order of operations. As we can see, if you're making note on what page to reference, this is on page 8 and 9. In fact, there's a little table on page 9 that talks a little bit more about that. So in our order of operations, some of you guys may remember when you were first taught this. If you don't, if this is new, I'm going to explain it. But if you were ever taught the phrase, "Please excuse my dear Aunt Sally," it was because you were taught to remember this little acronym up here on the screen. So some people may have been taught to remember the phrase PEMDAS, or again the sentence, "Please excuse my dear Aunt Sally." And what that stands for, if you're referencing this in your book, P stands for parentheses. So anytime you have any operation inside of parentheses, doesn't matter what it is, but if you have something along that line right there on the screen, if you're just looking at, again, an operation inside parentheses, we need to do that first. Again, the reason why we do this order of operations is because this states the order that we need to follow in case we're ever looking at a very large problem that has lots of different things involved in it, lots of different operations, and just lots of different calculations that we need to perform. This is what we're following. Then E stands for exponents. I'm going to talk to you guys a little bit about exponents. We're actually going to talk more about exponents in next week's lecture. But what an exponent is, anytime you have any number, and then at the top right-hand corner you have an even smaller number, what this tells you is to take that large number. So in our example here, 4 is what's called our base. So what that tells us, the exponent then, which is the smaller number, so what I've circled there in red, that exponent tells us to multiply that base that many times. So this can be read as 4 to the power of 3, 4 to the third power, or sometimes called 4 cubed. If you've ever heard 4 cubed, it's just referencing something raised to the power of 3. As oftentimes something raised to the power of 2 can be referenced as that number squared. If you ever hear that, it just means that it's being raised to the power of 2. So in our two examples that we have here, 4 to the power of 3 means to take 4 and multiply it 4 times. So not to be confused, 3 times. So not to be confused with 4 times 3, as we know that that would be 12. But 4 to the power of 3 means to take 4 times 4, which is 16, and then times 4 again, and that would give us an answer of 64. So that is 64. So that's what 4 cubed equals. Whereas 4 squared, that next one, just says to take 4 and multiply it 2 times. So in that case, that would be 4 times 4, which is 16. So again, not to be confused with 4 times 2, which is 8. This is 4 to the power of 2, and that is 16. Okay, so moving forward a little bit here, so I want to actually get rid of some of the stuff on here. Let me rewrite what we had up there. Again, we're following, "Please excuse my dear Aunt Sally." P, we just talked about, stood for parentheses. E stands for exponents. M and D stand for multiplication and division. Notice I put those two together. What that means is, at this point in the calculation, in the problem that you're working with, what we're going to do is we're going to read that from left to right. Just like we do when we're reading sentences in a book. We read it from left to right, and whichever one of those happens to come first, we are going to calculate that first. So in the event, let's say we're left, what we're looking at, the problem says maybe 8 divided by 4 times 2. It's so tempting to want to think that because in our mnemonic device, the "Please excuse my dear Aunt Sally," that we use to remember this order of operations, oftentimes people think because my comes before dear that we have to do the multiplication before division, and that is not the case. So it's tempting to want to take 4 times 2 in this problem first, and then take 8 divided by that answer, and that would be 1. 1 would actually be an incorrect answer in this problem. In this case, what we're going to do is we're going to read that from left to right when all we're looking at is multiplication and division. And we're going to read that from left to right. So in this case, 8 divided by 4 comes first. So when we take 8 divided by 4, we know that that's 2. And then we take that answer and then we multiply it by 2, the last one that's left over there. So that 8 divided by 4, that 2 was my answer from that. So that's 2, and then we'll take 2 times 2, and that gives me an answer of 4. So this is the correct answer for this problem. And now if it said 8, if I rewrote this here, and let's just say it said 8, just mixing that up. Let's say, let me get my blue pen here, 8 times 4 divided by 2. In this case, the multiplication does come first, because now when I read that from left to right, I now have 8 times 4, so I'm going to go ahead and do that first, and then divided by 2 is the last step. This answer would be 16. So that's what I mean by that. We're going to read that from left to right, and whichever one comes first is what we do first. And the last part of the order of operations, the A and the S, we do the exact same thing for both addition and subtraction. In that case, addition doesn't always come before subtraction as we think it might because of our please excuse my dear Aunt Sally phrase. Instead, when we read it from left to right, whichever one comes first is the one that we are going to calculate first. So when we use the order of operations, if say I have just, again, a long problem that says, let's say 20 divided by, let's say parentheses, 8 minus 3, and then let's take that and say we're going to add 4, and then say times 6 minus 2. I don't know. Maybe we've got a long problem. Well, let's call it, I want to add an exponent in there. Let's say 2 to the power of 3. Okay, so we've got all kinds of things in this problem on the screen here, and I need to solve this. The correct way to solve this would be to follow that order of operations. So thinking back to, again, PEMDAS, or please excuse my dear Aunt Sally. So this says that we need to calculate any parentheses first, any type of operation that we have inside parentheses. And we do have a parentheses problem in here. What happens when you're going through the steps, like if you get to parentheses, and if there aren't any parentheses in the problem, then you would simply just move on to the next step. In this case, we do have parentheses, so I'm going to solve that. We know that this right here, 8 minus 3, is going to give us 5. So what I'm going to do, and what I suggest to you guys when you have long problems like this, is to solve each problem one at a time, and then rewrite what you have left with. So, solve each step one at a time and then rewrite what you have left. So when calculating that 8 minus 3 to be 5, that means what I'm left with is 20 divided by, if I could write here, 20 divided by 5, there's that answer. And then there's the rest of the problem, plus 4 times 6 minus 2 cubed. So now that tells me what I have left with, and that means I'm finished with that first step, and I can move on to now the next step, which says E for exponents. And we do have an exponent down at the very end. 2 to the power of 3, remember, means to take 2 and multiply it 3 times. So 2 times 2 I know is 4, then 4 times 2 would be 8. So that means I'm left with 20 divided by 5 plus 4 times 6 minus 8. And see, what we're doing is we're shrinking this as we move along and now making it to where we have less to do. And that's the idea here. So now the next step, so we're finished with the exponent there. We've solved all exponents in the problem. Now moving on to the next step, which, remember, both of these together is multiplication and division. So I'm going to read this from left to right, and it looks like I do have a division problem that comes first, that 20 divided by 5 here first. We know 20 divided by 5 is 4. So that means I'm left with 4 plus 4 times 6 minus 8. Okay, so I know we're still on this M and D up here because we just solved the division, but now it does look like we are left with a multiplication now, and there's 4 times 6 right there in the middle, so I'm going to go ahead and solve that one, and then we'll be left with 4. We know 4 times 6 is 24, and then minus 8. All right, so we're finished with the multiplication and division. Now moving on to the addition and subtraction, and that's all we have left. That should always be our last step, and again, we always read that from left to right. So 4 plus 24 would come first. 4 plus 24 I know is 28, and then 28 minus 8 is going to give me 20. And so that's how we use that order of operations. More than likely, guys, on your all's quiz next week, you're not going to have anything as long as this, but this was great practice to see how we would take it one step at a time. So like I said, if you don't have that particular step in that calculation, what you can do is just move on to the next step. So say if you solve all your parentheses first, and then maybe you move on and you notice there aren't any exponents, that means you simply would just move on to multiplication and division. And it's important, you always want to make sure you follow this order of operations to make sure you're getting the calculation correct. Okay, so that was our order of operations. You'll see lots of practice problems in your e-text. If you're looking at that in the back of that section, you'll see some practice with the order of operations, and you'll see quite a few with your on your ALEKS homeworks. On your ALEKS homework. I do want to show you guys just one more thing before I forget. In our order of operations, so let me get all this off the screen here. So in our order of operations, again, please excuse my dear Aunt Sally. E, we know, stands for exponents, but E also stands for not just exponents, but also roots. Exponents and roots. And let me show you what I mean by that. So we talked so much about exponents, and again, we're going to talk a lot more about exponents next class. And how, like 4 squared, we talked about, meant to take, this was the same thing as 4 multiplied 2 times, and so our answer for this was 16. A root looks like this. If I ever ask you guys for the square root of 16, I'm using that because of what we just used as our previous example here. When I'm asking for the square root of a number, there is such thing as like a cubed root, or, even further than that, but all I'll ever ask you guys is for the square root. And that's just this little bracket right here. If you ever see a cubed root, you might see a little 3 over here, and again, I'm not going to do that. Just this plain bracket right here just means the square root. This whole thing up here at the top, oops, I'm erasing it. Up here at the top has nothing to do with this question, but because we just did that one, this example up here is going to help us with this answer. Down here, square root of 16, what I'm looking for when I'm looking for the square root of a number is I want to know what number squared will give me what's inside this bracket here. Because of the example we just did previously, we know that 4 squared is equivalent to 16. We just saw that answer. So that means 4 is the square root of 16, because it's this number that can be multiplied by itself one time, and that would give me the answer inside that bracket. Another example, for instance, then, let's say I ask you guys for the square root of, say, 36. What number can be multiplied one time by itself to give me 36? Well, that would be 6. And most of these guys that if I ever have a square root inside of a problem, it will be something like this that you can easily find the answer to. Yes, you can find the square root of 35, but typically you're going to need a calculator or some help with some factoring. Speaking of factoring, I do want to show you guys when we talk about the square root. So again, I can easily find the square root of, say, 81. I know that would be 9. The square root of 25. That would be 5, because again, it's 9 that can be multiplied by itself only one time, so meaning 9 times 9 will give me what I'm trying to find the square root of, so that's why the answer is 9. Same thing here, I'm trying to find the square root of 25. Well, it's 5 times 5 that gives me that answer, so that's why 5 is my answer. The square root of, say, let's say 49. I know that 7 times 7 gives me 49, so therefore the square root of 49 is 7. So those are the ones you're going to see from me. I do want to point out on your homework, just speaking of factoring, there is an example you may come across on your homework. I do not put these on the quiz, but I think I liked the practice of it. And at first, when I started teaching the algebra class, I did like this, but I really don't see this being something that you really have to stress too much on, as it doesn't really help us with what we're going to work on continuing forward. But if you ever see something like this, so let's say I ask you for the square root of 80 over 45. So even if I took, just to try and solve this, if I took 80 divided by 45, that gives me 1.77777. So I can't find the square root of 1.77777. But what I can do is I can find the answer to this a little bit easier. I can simplify it, at least. And how I can do that is I can factor out both 80 and 45. What I mean by factors is I'm thinking of what two numbers I can multiply by that will give me 80. So for instance, like 8 times 10, I know is 80. I know that 16 times 5 is 80. I know that 2 times 40 is 80. So I mean, I could go on probably a little bit longer here, but all these things are considered factors. That's what gives me. All of these problems here would give me that answer of 80. What I want to do is I want to do the same thing for 45. Yes, I know that 9 times 5 is 45. I know that 15 times 3 is 45. Looking at just what I have on the screen right now, here's how I can factor this out. What I want to do is I want to pick a set of factors where one of the numbers of the two that I pick, I can easily find the square root of, meaning the answer will give me a whole number. And then the other one matches one of the factors on the bottom. So for this example, what I mean by that, if I pick 16 and 5 and 9 and 5, let me show you what's going to happen here. And I'm going to show you why I chose those numbers. Oh, I didn't mean to delete the whole thing. So again, we're looking at the square root of 80 over 45. So let me show you why I picked those factors. Because what I can do is this is how the explanation is given to you on the ALEX homework when you see these types of problems. This is the same thing as taking the square root of 80 divided by the square root of 45. So if I were to just factor that out just right now. Then, breaking that down even further, well, the square root of 80, I just said that that's 16 times 80 is the same thing as 16 times 5. So let's factor that out a little bit further. That would mean that I could take the square root of 16 times the square root of 5. Because 16 times 5 were my two factors, it would work out the same way. The same thing again, down at the bottom I chose 9 and 5. So I'm just factoring out a little bit further here. So what happens in this calculation, because 5 and 5 are identical there, because they anything that's the same when we're looking at the top and the bottom of a fraction like we have here, so numerator, denominator, when they're the same, they pretty much cancel each other out. Because anything over itself is equal to 1, and that doesn't have to be written. So that's just assumed. And so when that happens, we can cancel those out, which means I am left with, and I'm going to write it down here at the bottom in green, I'm left with the square root of 16 divided by the square root of 9, and these, as we were practicing with those before, these are two numbers that I can easily find the square root of that will give me a whole number. I know that the square root of 16 is 4, because it's 4 times 4, that will give me 16. I know the square root of 9 is 3. I don't have to draw these brackets any longer because I'm actually answering that question. The square root of 16 is 4, and the square root of 9 is 3. So therefore your answer is 4/3, or 4 over 3, or even if you reduce that even further, you could call that 1 1/3. I mean, I'm sorry, not 1 1/3. Yeah, it would be 1 1/3. Or 1.3. If you took 4 divided by 3, it would give you 1.3 repeating, and you can call that 1.3. But in your ALEX assignment that you guys will see today, if you get a question like this, this is the answer that it's looking for. It's looking for that 4 over 3. So just if you see anything like that, like I said, I don't tend to stress on these. I do think I have one of these on your all's quiz next week as extra credit. So that's why I wanted to show it to you, because I think once you kind of get the swing of it and you kind of know, oh, okay, it's just a matter of factoring, it's really not too bad, and it could give us an opportunity for extra credit. So that's why I want to show you that. So just in case you guys come across something like that when we talk about the square roots. So the next section that you guys are looking at in your text, we're looking at solving algebraic expressions. So algebraic expressions, the difference between an algebraic equation and an algebraic expression is this. If you ever see something like, if I have 5x plus 2, that is called an algebraic expression, whereas if I have 5x plus 2 is equal to 10, Well, now that's different. This is called an equation because of the presence of this equal sign. So what we're looking at in this next section, we're just simply simplifying algebraic expressions. And this is something we'll get more into in the next couple weeks as well, that anytime we have an expression, so again, just something short and sweet, there are different things that we can do in different properties. So pages 10 and 11 in your all's text, when you go back and reference that, give us lots of different properties on ways that we can simplify terms. It gives us the commutative property, the associative property, the identity property. I mean, there's all kinds of different things. Pretty much with addition and multiplication, it's pretty much just telling us that with both addition and multiplication, you can reverse the order and it doesn't change the problem. So this is something we may see a little bit later too. So meaning if I had, say, 4 plus 2, 2 plus 4 is the same thing. So that's pretty much what the commutative property is saying. And the same thing goes for multiplication, that 4 times 2 would also give you the same answer as 2 times 4. I can't do that with subtraction, as 4 minus 2 would be 2, but 2 minus 4 would be negative 2. So that doesn't necessarily work with subtraction, and the same thing for division. So all of those kind of show that, and those are, I think, for the most part, pretty self-explanatory, and we'll get a little bit more into that later. But I want to point out the distributive property. The distributive property is the last property that they talk about. And this is something that we will work with a little bit more so in a couple weeks as we get more into our linear equations. What the distributive property says is that if you ever have, say, a number outside of parentheses, and the parentheses has maybe a different problem in it. So they use letters to show this, but if you have, say, 5 times x plus 3, I can simplify that a little bit further. Even so, if I showed you what it would be as a number, so let me actually erase that x. I want to show you how, if it's a number, yes, you can do this different ways. So say if it said 5 times 4 plus 3, well, our order of operations says that we would solve those parentheses and call this 5 times 7. Oh, well, that's 35. And so we could do that. We could solve it that way, but we would get the same thing if we apply the distributive property. And the distributive property says this, that what you can do is you can distribute that 5 to both parts of the equation that are inside the parentheses. So meaning that this 5 is, yes, being multiplied by this whole thing, so you can distribute it one at a time to kind of simplify this. So showing you guys that. So if I took 5, then multiplied it by just 4, we know 5 times 4 is 20. And then 5 and multiplied it by 3, whenever you see an operation symbol inside parentheses like this, look at it as that positive integer. So the plus 3 indicates that we're looking at 5 times positive 3. If it was minus, you can look at it as negative 3 and apply it that way. Is that something that we will get to when we get into some problems a little bit later? So that'll make more sense when we get into those problems. But that's something you need to think about, especially when we're applying this distributive property here. So 5 times 3, I know, would be 15. So this is the same thing as then 20 plus 15, which is 35. So yes, we could do it either way, but when you get variables added into the picture, and variables, for those of you guys aren't familiar with variables, is what I just had up on the screen there, is when we use a letter in place of an unknown number. So because I don't know what x is, I can't really do anything with it. I can't completely solve this problem. But to apply the distributive property, I can simplify it a little bit further. And that's all we're doing so far. We're not going to solve these whatsoever when you have these variables present inside these equations. I just simply want you guys to simplify these. So what that means is I'm going to apply the distributive property. So 5 times x would be 5x, and 5 times positive 3 would be plus 15. And that is the answer. That's it. That's all I want you guys to do on these types of equations. If you have, looking at ones that are a little bit more elaborate than that, so say if I had, I don't know, just say, let's say 4 times 3x squared plus 2x minus 5. I can apply the distributive property to make this, again, just more simplified to where it's just one linear expression and it doesn't have those parentheses in it. The purpose of the distributive property is it helps to remove those parentheses there to make it a little bit easier to work with. And that's going to help us when we get into solving our linear equations. Okay, so let me show you. So if we applied that distributive property, so we're going to take 4 times 3x squared. Well, 4 times 3 is 12, so this would then become 12x squared. That x squared just remains the same. Then when we distribute to the positive 2x, 4 times 2 is 8, so this will become 8x. Again, the x just stays the same. 4 times negative 5, we'll look at that as a negative 20. We'll call that minus 20. And that is our answer. And that's the only thing you're going to see there. I do have an example that may come up on your ALEX homework when you're applying this distributive property here. I wrote down this example. If I have, say, minus 2y, or negative 2y, I'm sorry, minus 6, and then in parentheses we have negative 4z plus 5y plus 3z. Now this looks crazy, but what happens here, we're seeing two different variables. We're seeing the letter y and the letter z. So just to kind of show you the difference there, I'm going to put the y's in red, and then the z's will remain. Actually, let's put the z's in green so you can see that they're two different letters, so therefore they are considered what's called unlike terms. You cannot put together unlike terms. We can, however, apply the distributive property first to remove those parentheses, because 6, right here in front of the parentheses, that number is being multiplied by everything inside the parentheses. So let's simplify that by applying the distributive property. So we're going to do that first, and I'll show that in blue. So this, again, look at this minus sign as a negative. So this is negative 6 times negative 4, and we know a negative time. That's why this is going to be really important when you look at that as those minus signs as a negative, because this is going to be really important when applying the distributive property, because we know a negative times a negative is a positive, and this is going to really affect your answer. Once we get into these linear equations and actually get into solving these, you want to make sure we visualize it that way. So I'm going to leave the negative 2y here, as we're not doing anything with that just yet. But negative 6 times negative 4 is positive 24, and then the z is going to stay, so that's 24z. And then the next part of the distribution is going to be negative 6 times positive 5, which is negative. I don't know why I wrote that. Which is actually then negative, let me get that black marker here, 30. So that's going to be negative 30y. And then the 3z I'll also just leave here. So once again, now we've got it to where we've at least eliminated the parentheses, and now I can completely simplify it as much as I can is the idea here. And again, I can only put together I can only put together like terms. So those red y's are what we can put together, and then the z's are what we can put together. And typically, you want to put the bigger number in front. So like when I add together those y's, not that it really matters. It's going to end up getting to where, especially when we start having exponents on there that we're putting in, it's really the bigger exponent. So this doesn't necessarily matter. So these are going to be put together here first. So the negative 2y and the negative 30y, we know negative 2 plus, and that's what we're doing. We're putting them together, so we're adding them. Negative 2 plus negative 30, it's a negative plus a negative, so that would be negative 32y. And if you did put the z's together first, that would not matter. I was simply thinking of exponents when I was saying that, so I don't know why I said that. But now I can go ahead and put together the z's, so we're going to go ahead and do that. So that would be positive 24z plus positive 3z, so a positive plus a positive is going to also equal a positive, so that would be plus 27z. And I cannot simplify that any further because y's and z's cannot be put together. Again, they're considered unlike terms, so this is our final answer for that. So that's how we would apply the distributive property on next week's quiz. It's something of that nature. I'll give you guys a problem where you just have to simplify it, and your answer is going to be something along these lines. So it's not going to be just a single number as your answer. I'm looking for just the simplified expression, and that's what we're looking for there. With these, I do want to show substitution. This is something that will probably come up on your ALEX homework. If you have, once you get it down to a simplified expression, if I showed you, so if say you get it down to, say, I'm trying to think of an example. When I have, say, 4x plus 7. If I have something like this, this is just a basic, simple expression. Again, I cannot solve for x since I don't know what this expression is equal to. There's nothing on the other side of the equation, so I can't solve this. But what I can do with expressions, once I have something like this, is if I say, okay, well, I do know, like if I gave you this problem on a quiz next week, and I said, let x equal, let's say let x equal 5, then would I be able to solve this problem? Absolutely. This problem up here says that 4 times x plus 7 is just my expression. I would be able to solve this if I knew what x was. Well, now I do. So substitution means that I can take what that is and substitute it and just plug it in to the expression here. So 4 times x would be the same thing as 4 times 5 in this. And then I'll leave that plus 7. And then don't forget we solve using our order of operations. So 4 times 5 would be 20. And then plus 7, the answer to this, we can figure that out, and that would be 27. So you might see some substitution being added on next week's quiz, and you'll probably see that on the ALEX homework too. So even if I had a couple x's, so meaning if I had, this is one I saw on the ALEX homework the other day, x squared plus 8x plus 2. If I said let x equal negative 5, then that means what I can do is I can substitute negative 5 into every part or everywhere I see x in this equation. So x squared means negative 5 squared, and I sometimes substitute using parentheses to show that x is, the whole thing is negative 5, so that whole negative 5 is being squared. So that would be negative 5 times negative 5 plus 8 times negative 5 plus 2. Now I should be able to solve this. So I'm going to do so in red down here at the bottom. Negative 5 times negative 5. Again, remember, negative times a negative, they're the same sign, so that means positive answer. So therefore that would be 25 plus, now here's a positive times a negative. 8 times 5 I know is 40, but because it's positive times a negative, it would end up being negative 40. So you could either write that as plus negative 40, or even if you wrote 25 minus 40, that would be the exact same thing. So it doesn't matter how you wrote that. And then there's your plus 2. So now our order of operations would be to then just read this from left to right, which says 25 plus negative 40, or again, if it said 25 minus 40, that'd be fine too. But 25 plus negative 40 would be negative 15. I'm running out of room down here, so let me just write this in blue up at the top. So it'd be negative 15 plus 2, which we know is then negative 13. So we'd be able to completely solve that when we use substitution. So that's substitution. It's just a matter of just substituting in when we're told what our variable is equal to. And the last thing that you guys are going to see on this, in this lesson, or for this week, is over on page 12, it says writing algebraic models. And that is simply just taking word phrases and putting it into an expression of some sort. So either a sentence or perhaps a word problem. So it could be a couple sentences, and we're turning this into an expression or an equation of some sort. So a great example would be, let's say, they use, I'm grabbing an example that they have in the book. So I'm going to read this sentence to you. So if you need to go back and listen to what I've said again, I'm not going to write it out on the screen. It's much easier to see it. This is, if you are going to go back and reference your text, it's page 12, down at the very bottom, example 10, letter A is the one that I'm looking at. So this says that the maximum recommended heart rate, and then they give the letter M, showing that this is the variable that you want to use for that. So this is referencing, this is the maximum, so I'll just write this as max heart rate. so we know what we're talking about here. The maximum recommended heart rate, M, for adults is the difference of 220 and the person's age. So it says to write a model to represent that maximum recommended heart rate. So to represent what we're looking at here on the screen is the letter M, and it said for adults it's the difference of 220 and the person's age. We know the difference means subtraction, so the maximum recommended heart rate, so we could say M is equal to 220 minus A for age, and that's the letter that they had us use for that. So this would be the answer to this. So that shows us how we could write that as an algebraic model. We're simply just taking sentences and turning it into an algebraic equation here. Another example, and I wouldn't give you one like letter B. I'm not going to do anything that has where you have to use greater than or less than or anything like that. It would be equal or equal to. So like skill practice 10 on page 13. So skill practice 10 on page 13, letter A says the sale price, and they said to use S to represent sale price. The sale price on a lawnmower is the difference, so there's that word difference again, so we know this is going to be a subtraction problem, is a difference of the original price P and the amount of the discount, D. So it says write a model to represent the sale price. So here's the variables they want us to use in this equation. And it says the sale price is, so in other words it's equal to, the difference of the original price, so here's our original price, and the discount. So that would be minus the discount, which makes sense. Anytime something is on sale, it's always the original price, and then you subtract the discounted price. And so that would be the algebraic model for this. And letter B, the amount of simple interest, so they said to use I for interest. Interest earned on a certain certificate of deposit is 4.65%. Now the hard thing with percentages, and I probably won't give you percentages, is you have to represent percentages as a decimal, because 4.65%, if I was to multiply that by anything, this percent symbol can't be recognized by a calculator. So how a calculator recognizes a percent is if you write it as a decimal, and that would be a matter of just moving that decimal 2 places to the left. And so really we won't see that come up too much until really the last lecture in algebra, when we deal a little bit more with percentages. So that would be 0.0465. So just kind of a heads up on that. That's what we're going to use in this particular problem. Like I said, for next week's quiz, though, I'm not going to give you guys any percentages. So this is just an example I want to show you guys, though. So letter B says the amount of simple interest, so again, I, earned on a certificate of deposit is 4.65% of the amount of principal invested, which is P. So how we would do that is simply just take that percent, so that's going to be I is equal to that decimal, 0.0465, and multiply it by P. So anytime you're multiplying a number by a letter, a variable, you can just write them right next to each other, and then it's understood that that's what that represents. So that's how I would write out that algebraic model. So what you'll see on next week's quiz, guys, I do some simpler ones, very similar to that sale price example that we just did, maybe short and sweet like that one. And so one that you'd be able to kind of understand how to write it as an algebraic model. But that's what that is simply just taking a couple sentences, so a word problem, and turning that into an algebraic equation. So you'll see some practice with that, either in your text for some practice problems or on the Alex homework too. You'll see a couple with that. All right, guys, if y'all have any questions, let me know.